Hi, my name is Isidro de Leon, and today I'll show you something about the investigation I've done in the first part of my PhD thesis. The title of this poster has the name Effect of the 3D Printing Design in the Catalytic Activity of Monolithic Catalysts. Let's go for the introduction. As we know, catalytic processes are the dominant driving force in the chemical industry. So, working on the proper design and manufacturing of three-dimensional catalyst monoliths favors the active species dispersion through the catalyst surface with the advantage of exposing abundant active catalyst sites. Furthermore, the formation of turbulent flows in continuous flow reactors is promoted, and this leads to improve greatly the catalytic performance. Additionally, the main advantage of three-dimensional printing technology, also known as additive manufacturing, is the opportunity to provide free design and precise manufacturing of complex 3D structures in both efficiently and economically ways. The three-dimensional printing technique is a manufacturing method that is within the recently merged Industry 4.0, and the applications for 3D printing technologies have expanded enormously due to the decrement in the development and operating costs at the industry itself. Catalyst fabrication is a promising area for 3D printing, as printing processes result in better control of the structures and distribution of active sites in the catalyst. In this sense, there are several 3D printing techniques such as extrusion printing, direct ink printing, bath photopolymerization, stereolithography, among others. However, from the high-precision printing techniques, stereolithography allows printing reactors and lab-on-a-chip devices like monoliths that we are printing for this work for efficient chemical reactions with reduced absorption of reagents. However, in the world of chemistry, until now, miniaturization has played a minor role. The chemical and thermal stability of normal 3D printing resins is insufficient to withstand the harsh conditions of chemical reactions, which is why the development of new formulations of resin-based materials is sought with the use of noble metals like palladium or platinum that favor the development of highly stable 3D printed devices at low working temperatures to update the chemistry in the development of miniaturization. The objective of this study is evaluate the design effect of 3D printed monoliths impregnated with palladium on its catalytic activity in the oxidation process of toluene. The methodology we followed starts with the 3D printing of three different monolith designs named as MN1, MN2, and MN3. Figure 1 shows their designs here. And then we followed the next 4 steps. A, impregnation. B, thermal treatment. C, characterization. And D, catalytic evaluation. The impregnation was realized preparing one solution of palladium chloride containing 1% of palladium, with the monoliths placed both in a beaker where they were heated to dryness at a temperature of 85 degrees Celsius and under magnetic stirring, as you can see here in this part. Once the monoliths were impregnated with palladium, they were treated thermically at a temperature of 310 degrees Celsius by 5 minutes. And then afterwards, the monoliths were ready to be characterized by SEM, FRC, scanning electron microscopy by EDS, energy dispersive X-ray analysis, and XRD, X-ray diffraction. Finally, in the last part, the catalytic evaluation for the degradation of toluene was done with the conditions of GHSV of 10,500 hours minus 1,000 parts per million of toluene, and reaching a temperature of 300 degrees Celsius in this catalytic process. Let's go to the results and discussions in the part 4 of this poster. The first ones are those for SEM and EDS. In the figure 3, we can see the same micrographs from the 3 different monolith designs impregnated with palladium on its external, the micrographs in the superior part, and the internal, the micrographs in the inferior part of this micrographs. The images in the internal surface were achieved doing transversal cuttings at the half distance on the height of every monolith. In these same micrographs, we can clearly observe the differences in the channel designs and dimensions, but overall, the homogeneity with palladium impregnation. In the table 1, EDS analysis obtained for monoliths, we see big differences related to its 3D designs with a media between the palladium charge in the exterior and the interior surface of monoliths of 16% for MN1, 34% for MN2, and 36% for MN3. As we can see, the MN3 design got a better impregnation of palladium on both the internal and external surfaces, taking these results as a reference. In figure 4, we can see the characteristic signals for palladium according to the target JCPDS 050681. This means the methodology followed for the impregnation and thermal treatment allows a good dispersion of palladium in the monolith surfaces as we see it too in the same micrographs. In the last part of these results, the most important ones, we can determine which of the 3 designs has the best catalytic efficiency in the oxidation process of toluene. In both figure 5 and table 2, we can observe the CO2 conversion or carbon dioxide conversion percentages of monoliths MN1, MN2, and MN3 for the oxidation of toluene. The results can be explained in function of the design, the turbulence generated with the monoliths, the palladium charged media, and the crystallinity of palladium in every monolith. Monolith MN1 has the poorest catalytic efficiency due to the conventional flow who limits the turbulence within the monolith. The low palladium charged media is found in this design. That means it has lower active sites in its internal and external surfaces, and the crystallinity is the lowest too. On the other hand, this is the one for MN1. On the other hand, for the MN2, the red line here, this describes the behavior for the best design. Monolith MN2 presents the best catalytic activity with a T90 of 241.21 degrees Celsius. This behavior is explained due to the turbulence generated in the cross sections of the channels and the residence time of the gas flow within the monoliths. So these factors, in combination with the best crystallinity and good homogeneity of palladium in the internal and external surfaces, makes it the best 3D printing design. And this is all for the part of results and discussions. The conclusions of these investigations are: some results show 3D monolith designs are printable and palladium impregnation is achieved on its external and internal surfaces. X-ray diffraction patterns indicate the monoliths are impregnated with palladium after the thermal treatment, and the MN2 reached a major crystallinity among the 3 designs. A major crystallinity leads to a better catalyst monolith. The design of 3D printed monoliths affects their catalytic activity due to the differences in their surface area, but the turbulence generated in the cross sections of the channels and the residence time of the gas flow within the monoliths are probably the major factors who sets the best catalytic activity. In base of the results obtained, the MN2 monoliths presents the highest catalytic efficiency in the degradation of toluene with a T90 of 241.21 degrees Celsius at a GHSB of 10,500 hours minus 1. Finally, I want to give my acknowledgements to the Environmental Engineering Department and the Laboratory of Construction Materials Characterization from Universidad Autónoma de Nuevo León, Facultad de Ingeniería Civil, for all their support in the characterization of materials in this work. This work is currently supported by the project CEP, concept number A1S13217. And this is all for this moment. Thank you very much.